could spend a whole course on. In fact, I think there are courses on models. What I'd like to do today is to describe their application and strengths and weaknesses and the general approaches that are used in modeling. First of all, I should say that models are not new. Numerical models are new. Well, even numerical models aren't new, but our ability to use them is new. In 1957, I think it was, I developed a numerical model for a canal using a mechanical calculator. And I remember a project that, as you can imagine, is a pretty simple model. I remember a project where a young lady spent all summer, 3 months, punching in mechanical calculators to calculate the tide going through a proposed sea level canal across the Isthmus of Panama. And whenever she made a mistake, she had to go way back and once again, it was a real difficult project, and it was the simplest model you can imagine. I mean, it's just a very simple one-dimensional model. But 40 years before that, hydraulic models were put into service, and the early ones were just very small models. For an estuary, it would just be on the order of a few feet. But then the art improved and developed to its highest level in about the 1950s, when hydraulic models like the one we saw in San Francisco were developed. The similarity criteria were developed so that you could relate currents measured in the model to currents in the prototype. The use of saline water in the ocean and fresh water in the rivers was used early to show the intrusion of salts into an estuary and to show the effect of the salt water on the circulation in the estuary. And the technology, it's really not so much the technology as an art, was pretty highly developed. Some used rosewood in Wallingford Hydraulic Research Station, for example, in England. They used rosewood granules to simulate sediment. And in San Francisco Bay model, they used saturated gilsonite coal grains to simulate sediment. But what they found when they did that was that it didn't simulate very well. In fact, it turned out that it only simulated scour. It didn't simulate transport really at all. That is the general movement. The use of numerical models, as I said, began really in the 50s, about the 1950s. And their utility has grown with the availability of vast number crunchers, computers. And the fact that now that every desktop has a powerful computer, as far as the modeling is concerned, has just revolutionized the development of models. But I must say, we're not there yet. You know, models have a long way to go, and if you get a room full of modelers, about this many modelers, you get this many opinions on you know, what's the best way to model and what the problems are and so forth. So even though there are many models out there and there are quite a few people using them, they're still not developed to the point where you can just say, put numbers in this model and it'll give you answers. You know. In fact, as you'll see, there's an awful lot involved. A lot of the knowledge of the system required to interpret a model correctly. Well, models are used to evaluate alternate design. Maybe I should write these uses. Such things as harbors, channels, reservoirs, that is dams, and training works, all kinds of hydraulic works can be evaluated using models. And the idea is to try a design, model it, and try to look at alternate designs and compare their models, you can usually find optimum costs or best performance or difficulties that you hadn't anticipated from the use of models. A second use is to plan monitoring programs. And this can be generalized to other kinds of measurements too. But often it isn't apparent. It's just looking at a system where the really sensitive measurements can be made. And by using a model, you can see where changes are important. For example, it may be that changes are really important over an oyster bed, and it may be that it's some other oyster bed that they're really important over. There's currently a study going on in Galveston Bay on the effect of salts on oyster production. And it isn't intuitively apparent how the salts move in and out and what the effects of freshwater flows are. But with a hydraulic and salinity model, you can see where the salts are going and see what the effects of different mitigating works are. A third reason is for management. Of water resources. And I mean resources in most general sense, not just water supplies. And for example, flood control. When you design a reservoir, how big should the reservoir be? You know, what's the benefit of raising the dam higher? Well, you can evaluate the effect of more or less storage on downstream flooding. You can evaluate the amount of reservoir capacity that has to be kept available for floods and not used for storing water and so forth. And of course, the Federal Insurance Management Agency, FEMA, Federal Emergency Management Agency, delineates flood zones for insurance purposes. And that's can be done by modeling. Water supply involves many aspects of hydraulic systems, not just volume of water, or volume at a given time, but also all the conduits and regulatory and storage, distribution storage facilities. Water quality. Manage water quality. And this can include such things as temperature, dissolved constituents, suspended constituents, biota, wildlife habitat. There are many aspects of water quality that can be modeled, and determining the optimum or even feasible management strategies can be done with the aid of models. Just as an example, the San Francisco Bay system, which I'll hope to talk about later, we have fresh waters that used to flow into the system, now are being used for irrigated agriculture and municipal and industrial uses. The San Francisco Bay water quality, or water body, at the same time is being insulted more and more by increased waste discharges. Even though the treatment's been improved over the years, there's still more and more of it going in. The fishery is dying. Some salmon runs have been lost. The striped bass fishery is the lowest it's been since striped bass were introduced. And we have some very serious problems. Well, you can't just stand here and say, we need so much water to go into the bay. The two obvious causes are reduction of freshwater inflow and increased waste discharges, as I mentioned. There are other factors too. But you can't say we need this much water without some way of determining quantitatively what the impact of more freshwater flow would be on water quality. You follow me? It's not a matter of yes or no, it's a matter of how much. And to determine how much, we need some kind of a calculation based on the system's actual response to the freshwater inflow or to reduce waste. So, then of course, I have to mention sediment. impacts of disposal. Marsh restoration, we talked about that the other day. I'll talk about it shortly. Contaminant transport. And power generation. I'm sure I'm not including everything, but I think you get it. Power generation sounds like it's a bit far out, but consider this. Whenever you build a dam on an alluvial stream where the sediment's being transported down the stream, the dam stops the sediment transport. So the stream scours out downstream from it. Got some serious problems with erosion and bank failure and so on resulting from putting a dam in. Another cohesive sediment application of power generation is the diversion of the Cooper River. It used to go directly into the Atlantic near Charleston, north of Charleston. It went directly into the Atlantic, but they found that there was a place where there was a significant elevation difference between the Cooper River and the Charleston Bay. So they built a power plant there and diverted the Cooper River into Charleston Bay. The result was huge accumulations of cohesive sediment, just incredible amounts of cohesive sediment. So now they're diverting the Cooper River back to the Atlantic. Problem. And then finally, after I have management, which takes up a lot of it, yeah, I'll put down for legal purposes. And an example of legal use is the data that I showed you on the history of marshes the other day. The titles to marshlands and submerged lands depends on the elevation of the marshes. If the marsh is above mean high water, then it's considered upland. And what body of law applies. And if it's below that level, another body of law applies. And it may, in fact, not belong to the state, or not have belonged to the state when they gave title to it, but actually belong to the federal government. So turns out that elevation of marshes, as one example, at historic times is of interest. Areas that are diked off now, you can't tell how high they were in 1850, when the land was, or 1870, when the land was, the title to the land was given to the applicant who applied for it. But by determining the elevation of marshes nearby and modeling them the way I described it, you can make a pretty good estimate of what the elevation was at any previous time. Well, the same thing applies to boundaries. Navigable streams by all over the United States and pretty much all over the world are considered land boundaries at the location of the high water mark on the shore. And if the stream accumulates sediment on the side, the boundary moves with the sediment. And if it erodes, the boundary moves back with erosion. So the position of the boundary depends a lot on what the stream is doing. The exception is if there's an evulsive event, a huge flood that comes through and just washes out everything. That doesn't count. The boundary stays where it was. Too bad it doesn't count, because that brings up a lot of lawsuits. And examples that I can tell you about are the Peace River in Florida, $2.3 billion lawsuit that involved 26 miles of phosphate mine. And the issue is the boundary of the mine the bank of the river that flows through the swamp, or is it the edge of the swamp? What's the ordinary high water line? And they're that far apart. There's that much land, phosphate mine involved.
Which river was that?
Peace River.
Peace River.
Now the case, the applicant plaintiff withdrew, but it involved a lot of money and a lot of time. And it's kind of an interesting story that a group of promoters got together and persuaded the state of Florida to assign to them the mineral rights of all the sovereign lands of the state of Florida. That's offshore lands, and so on. And they took that property, what it amounts to Mobil Oil Company, and said, if you'll explore for oil on this land, we'll give you half the value of the oil. That's a pretty good deal for Mobil too. So Mobil put in they agreed to go to $10 million. $10 million worth of exploration, which isn't a lot of exploration, but it was enough to punch some holes down and see what would happen. Well, they got in about $6 million worth of drilling, and somebody in the state of Florida got wise to this scheme and said, hey, the state can't give away mineral rights. So the state of Florida imposed on this consortium, it's called Coastal Petroleum, and said, hey, we can't do that. Well, Coastal Petroleum said, okay, we'll settle for half the rights, but the half we'll take for developing it. And Mobil Oil said, well, we've already put in more than half our $10 million, we're not going to drill anymore. So the whole thing fizzled. Coastal Petroleum was without any money, and nothing further was being done. So Coastal Petroleum brought suit against Mobil Chemical Company, alleging that the land between the riverbank and the edge of the swamp belonged to the state, and therefore the mineral rights belonged to Coastal Petroleum in the state. And that's where this suit came about. Well, I spent about 3 years working on it. We had a hydrology company and a couple of biology companies, and quite a few people working on it. We drilled deep holes, related the water to the surface water to the groundwater, surveyed the stream. I had the stream surveyed 3 times, and every survey had water flowing uphill somewhere along that stream. And we measured flows during floods and everything, and then finally the Coastal Petroleum withdrew their suit. Then, of course, we immediately sued for the cost of the money we put into the investigation. It never worked out, but it was an interesting case while it lasted. But anyway, what I wanted to say was that the modeling provides a means of quantitative determination of things like that. Like we calculated the elevation of water surface elevation for any given flow down the stream, for example. Well, models are simplified simulations of the hydrologic system that include the descriptions of the significant processes. And that's a key thing to models. They have to be simplified, or you wouldn't be able to handle them. So you remove the things that aren't important to what you're trying to understand, but be sure that you include all of the processes that are important. And of course, the descriptions that you provide are limited by the precision of your measurements. The number, for example, in water depths in an estuary, you can't measure every single point. So you make ordinary hydrographic surveys and include them with enough points and enough accuracy so it simulates the system. It represents the system pretty well. Well, I mentioned physical models for hydraulic systems, and numerical models have many advantages over physical models that are making them used more and more. One of the big ones, of course, is cost. It costs a lot less. You don't have to pay for storage and personnel while you're not using a physical model, a numerical model, whereas you do with a physical model. So let me sort of outline the approach of physical modeling that's used. The foundation of sediment transport and water quality and all these models that I described is a hydraulic model. And to this hydraulic model, you have to put initial conditions of IC and boundary conditions. We'll talk about those more later. That includes things like the configuration of the estuary or the river, whatever it is you're concerned with. Inputs, flows in, flows out, wind stresses on the surface. I'll write these down. And then in an estuary, that's usually coupled with a salinity model. And the hydrodynamic model describes the flows, the currents, the tides, and it also has initial and boundary conditions. And the salinity model is coupled back to the hydraulic model so that the density resulting from the change in salinity is represented in the hydraulic model, if it's a 3D model. Okay, we'll talk about that later. But the point is, they need to be coupled if you're going to, for a 2D laterally average model, so that the effect of changing salinity on the hydraulics is represented by the hydraulic model. Then a sediment transport model takes the current U, V, W, the shear stresses, bed shear stresses, and diffusion coefficients from the hydraulic model directly for the sediment. The diffusion coefficients come out of the salinity model usually. So this will be density out of this and diffusion coefficient. Then sediment transport model is coupled to a model of the bed, sediment bed. And of course, deposition goes to the bed, and erosion of the bed goes back to the sediment transport model. And then on top of this, I'll put a water quality model. And this takes information from the hydraulic model, U, V, W, D. I'll put D sub I because there'll be three of them if you do a three-dimensional model. And this has inputs, initial conditions, and boundary conditions. And under boundary conditions, I'll include inputs of various kinds. So you can see that the hydraulic model is the foundation really for all the rest of the model. After all, it's the water movement that moves the sediments and the dissolved material. So that the faithfulness of all of these other models depends on the hydraulic and salinity model in an estuary. And in a freshwater, it depends on the hydraulic model. And in freshwater reservoirs, instead of salinity, we'll have temperature, which will affect the density. So maybe I ought to put temperature here. And usually these two have to be coupled right in the modeling operation. That is, as you progress in simulation of the flows, you also progress in the movement of the density affecting factors. Now, if the sediment concentration is very high, then it too affects the density, and you really need to have coupling back for that one. I'll come back to that point. Well, these boxes contain an awful lot inside of them, and what I'd like to do is to describe, first of all, just simply what goes on in the hydraulic model and what's required to make one go. So the first thing we need to be concerned with is the hydraulic model. And let's start out with one dimension, keep it simple. So I'll describe the Sediment equation. Most of you are probably already familiar with these. The first one is continuity. That is conservation of volume. Water is considered to be incompressible. So when we talk about conservation of mass and conservation of volume, interchangeably. So continuity, and we have partial t with respect to x, plus the partial of a of y with respect to t equals 0. And this, I'll call this bottom slope s of 0, and the flow depth here y. And all this just says that any change in the body in the flow has to be reflected by a change in the storage in the local area. And then we have conservation momentum. And this is written in various ways, and I'll write it this way. Changing y with respect to x, plus the velocity u divided by g for gravity, changing u with respect to x, plus 1 over g, the change in u with respect to t, is equal to s sub 0 minus s of f, where s of f is the friction. And if you use Manning's, you can write s of f, the Manning's relationship, is equal to n squared u times the absolute value of u divided by 2.21 r to the 4/3. Or you can use Chesney or whatever else you like for friction. Now we're talking about a one-dimensional prismatic channel, okay? That is gradually very unsteady flow. If there isn't, because of this, the fact that u appears in here as a square, because you have this u to u, it's a strongly nonlinear system. So there isn't an easy solution, isn't an analytic solution to it, even for simple channels. So it's solved for numerically, and the terms are, this is the change in water surface elevation along the length of it, change with x. This is the acceleration term, the effective acceleration momentum. This is the, this is the acceleration term. This is the change due to the gradient. And then this is the bottom slope and the friction slope here. In order to solve this numerically, it's common to break up the channel, for example, in a marsh into short prismatic channels and calculate u in the channels and assume that the storage all takes place at the nodes. And so that you calculate the change in volume at the node and the currents in between. It's if you use what's called an explicit method, that is a time step delta t for your computation, it's necessary to keep the delta t times u sufficient to stay within a link. If it gets beyond the link, then it becomes unstable and the solution blows up. So-called criteria. Well, you can see that these are point equations. Points along a channel, and that the change in the lateral direction is average, that is, the current in the lateral direction is average and the current in vertical is average. So we're looking at a description where you just have you assume that the velocity is the same all the way across the channel, up and down, side to side, in a cross-section of the channel that's just moving along. It's a pretty crude representation, and yet it's adequate for many purposes. Still widely used. In fact, the Environmental Protection Agency uses this as a foundation for one of their water quality models. It's been back in the 60s, early 60s, when people still had to use punch cards to program computers. This was widely used, and it was used in what's called the linked node model, where you can not just have a prismatic channel like this, but take a large water body and consider it to be made up of a number of channels and calculate the flow in and out of each node. Oh, I don't have a very good representation, but you can see that you can represent on a lateral distribution a water body by assuming that it's made up of channels like this. So-called linked node model, still used today, still applicable for a number of situations. Very simple, can run on a fairly small machine. EPA's one is called WASP 5. And it includes they assume that the water in a block like this, some moves out and some moves back in and out the sides, and they calculate by just diffusion processes what the transport and advection what the transport is. Well, in order to run a model like this, it sounds simple, but in order to solve a problem using a model like this, it's first necessary to get all these boundary conditions I just erased, and initial conditions, and all the input. And it turns out that getting input to the model costs far more than running the model. I mean, that's really where the cost is. For example, in applying this one, first of all, let's take a marsh example. After applying this to the channels in the marsh and plugging on the marsh. In a marsh, the first thing you have to do is a topographic survey. Which is fairly expensive because you want it, in a marsh, you want it to be precise. You want it to within a tenth of a foot or so. Then you need to know the tides at the bay boundary. Of the marsh. The roughness of marsh channels. I'm going to talk about this some more too. Winds, perhaps, and you might want to, if you're calculating flow through the vegetation, you might want to know what the roughness is for the vegetation, that is the resistance. It's called, I'll put this in parentheses, the density of the sediment bed. And the suspended solids in the incoming water. Well, you can go out and measure topography. Even if you have to go out and do it physically, you can somehow get out there and measure it. And the tides aren't too much of a problem. If you don't have them, you can set up a tide station. But usually you can calculate it from the model of the estuary. Roughness of the marsh channels is not easy to determine. Somehow you have to determine that hydraulically. Winds you can get from records, and density of the sediment that you can get from cores, in cores. But the suspended solids and the incoming water vary continuously, so there isn't any easy way to get at that. In fact, they range typically over a wide range of concentration. So what's done is to go out in the marsh or channel system, wherever it is you're modeling, and make measurements of the tides in various places, a number of places in the marsh. Then crank up your model and adjust the value of n until the model reproduces what you measure. You follow me? And similarly, for suspended solids, you can take a core, measure the surface elevation accurately of where the core was taken, and simulate the accumulation of sediment, and back out the suspended solids, back out a representative suspended solids concentration for the whole system. So both of these are done by calibration. And it's a very good idea to take more than one, or take currents and tides under more than one tidal condition or freshwater flow condition. In fact, as wide a range as you practically can, to see that the model represents all those conditions. If it doesn't, there's something wrong with the model. You know, you want a model that it may be that you're overlooking some particular factor in the model. This is called calibration. And when you compare it when you run the model for other conditions and compare it to measurements for other conditions, it's called verification. You'll hear these terms. But actually, it's all one process, because if you run it under 3 different conditions, you want the model to represent all 3 conditions, and you wind up making some adjustments so it represents them best, or you find what it is that keeps them from representing various conditions. Well, you can see that it's an expensive process and time-consuming process. And when you begin modeling an area, it's a good idea to go out and look at all the information you can obtain about from a hydrologic standpoint. That is, records of what it was in the past, you know, what changes have been made, what the consequences of those changes were, what changes occurred naturally, for example, accumulations of sediment. Often you learn a lot about a system just by going back through the records, comparing hydrographic surveys, for example, and in a marsh, comparing old maps of open marshes. Then design the field exercise to get this kind of information. And usually that can be done in parallel with getting the model up. Sometimes running the model in a preliminary way will help tell you where you need to make your measurement, you know, what the most sensitive locations are for the measurement. The more conditions that you can verify, that is, more conditions under which you can demonstrate that your model works, fits actual measured data, the more confidence you have in its ability to predict what will happen under other conditions. Well, I described a one-dimensional model, and that's a model that we used with a mechanical calculator. That was all there was to it. Very unstable model, and I was really turned off to numerical models from that experience because it was so darn unstable and so touchy. The numerical methods are constantly undergoing development. About every 6 months, somebody comes out with a new way. You know, we have explicit, implicit solutions. We have multi-split mode solutions. We have finite elements, finite difference methods, finite volume methods. There's just methods coming out all the time to try to overcome some of the problems numerical problems in solving these equations. Let's say a few words about 2D and 3D models. 2D models have been widely used since the mid-70s. And they involve both continuity and momentum equations, just as we did in the 1D case. And they're important where you have where you can average one dimension and model the other two, where you need to model the other two. And a good example is wide shallow bays, where the density is fairly uniform, that is, vertically density is fairly uniform throughout the depth. You can parameterize the vertical velocity profile using logarithmic velocity profile. We don't have to just average it, you can represent it. And it provides for input winds as well as tides and currents and so forth. So 2D models provide a lot more, simulate a lot more of the forcing processes than you can do in a one-dimensional model. There are situations, however, where a two-dimensional model is not enough, where you really need the two dimensions. And that's particularly true in estuaries. In principle, you can represent mixing zones with the more dense water flowing up under the outflowing pressure water by using a two-dimensional model and laterally averaging. That is, modeling the vertical and longitudinal and averaging across the estuary. That's pretty successful in straight channels, straight narrow channels. But if the channel is very wide, then Coriolis effects become important. And if there are any bends in the channel, then you get internal tilting of the density gradient. That is, instead of just flowing upstream this way, on a bend it'll turn. It'll have centrifugal forces. You have Coriolis effects in wider bays, and the combination of more dense fluid near the bed due to salinity and sediment, suspended sediment, combined with bends in this where you make it really a three-dimensional process. And you make mistakes if you don't represent all three dimensions. So it's necessary to under some conditions, to do that. I don't think I'll write them on the board. Maybe I'll write one of them on the board. I passed out to you Peter Schenk, who's now at the University of Florida, description of models. It's a pretty good description. I don't subscribe to everything he said, but I suspect that he doesn't either now. This was 1983, 10 years ago. But he provides a description of models, and on page 20 he gives us a tensor notation, and I'd like you to turn to page 21, and I'll put just one of those on the board and describe what's involved. First of all, it has continuity, just like we had it before, u dx plus dy dx. Oh, and incidentally, the coordinate system is x, y, and the currents are u, v, w. U dx, dy, dv dy, plus dv dy, plus dw dx, dv, And then the momentum for each in each direction, I take the x direction, partial u with respect to t, plus u du dx, plus u v du dx. We should put the product in the derivative, which may be all right. This is dy, and this is dz. Is equal to fv, which is the Coriolis parameter, 2 omega sine phi times v, or the lateral effect, times 1 over rho 0 dp dx plus the change with respect to x of a of x du dx. You have this already written down, so this is a change. This is a point equation. It describes what happens at a point in the system, just at a point. The change with respect to time in the x direction. Of course, there's similar relations for y and z direction. The acceleration term, the effect of v on the change in the velocity in this direction as you go sideways. The effect of w on the effect of the lateral velocity as you go upward. This is the Coriolis force that pushes always to one side, depending on the velocity. This is the pressure that's driving the system. This is the driving force on the system, change in pressure. And it's assumed that the pressure is hydrostatic in this derivation. That is, we put pressure here, and it assumes that the pieces are there. The way this is written, it describes the pressure, the density as being uniform like that. And this one is the Wilson-esque assumption. And it comes about from, remember, Newton's hypothesis is that the shear stress is proportional to the velocity gradient. And for viscous flow, we said that you could describe it this way, Newton's hypothesis. Well, Wilson-esque said we should be able to describe the shear stress as, for turbulent flow, as a combination of the viscous resistance plus some other constant kind of resistance. This is the weakest part of this formulation, because as you can imagine, as we've discussed, vertical momentum transport in turbulent flow, the momentum transport changes with the flow. That is, if you have a higher velocity gradient, you get more mixing. So in solving this combination term is the weakest part of the whole thing, and it's where you often have trouble. Now, without this, you can't solve the equations. You need something here. And in the last 4 or 5 years, there's been some theories developed whereby the rate of energy production and the rate of energy dissipation is used to calculate momentum transport. It's it's called the K epsilon theory. What's it? What's it called? Anyway, it amounts to another partial differential equation calculating the rate of energy production and the rate of energy loss and the resulting momentum transport from it. It has 6 adjustable coefficients, so I'm not very happy with it. I'm not an advocate. But there are people who are using it quite successfully, and it must be that they picked the right coefficient.
How do they do that?
What's that?
So how do they actually sit and work with it and pick the coefficient?
They,
Like random?
they're arrived at, I think, by what works. But they seem to provide some pretty good results. There's a chief exponent of this named Rudy. He's now at Karlsruhe, I think, in Germany. Wolfgang Rudy. And he's applied it widely and has impressive looking results. Professor Rock has used it. It's called the K epsilon theory, but I can't, there's more to it than that. In any case, what's done practically is to use this and then make adjustments to this. And as you'll see, that has some other ramifications. So in any case, what we have is continuity and momentum transport at a point. Remember, these describe what happens at a point. So in order to describe what happens in a system, it's necessary to integrate these over the whole system, which are initial conditions and boundary conditions, all the forcing processes that go on, imposed, distributed over the system as it actually is. So even though you can develop numerical solutions to these equations, you still have the problem of getting the information that you put into it. And if the problem you're concerned with has to do with long periods of time, then you have to have the information over long periods of time. I'll describe some of that in a minute. Well, this is the hydraulic equations. And then the transport equations. Look like, I'll put it in terms of concentration, or it could be salinity, or you see the T plus CDF plus CDY plus W change with respect to X. D X change in C with respect to X plus change with respect to Y D sub Y C Y plus change with respect to Z Z plus sources. This is a well-known advection dispersion equation in 3 dimensions. And this is the change in concentration with time at a point. This is the advection term, that is the movement of the material as a bulk in the system. This is a dispersion term. That includes the effect of mixing in the water body. Vertical mixing, lateral mixing, and longitudinal mixing. And the sources and sinks are deposition and erosion, or a material brought in by stream, for example, in the case of sediment. For salinity, it's the ocean, salinity of the ocean, and the movement of ocean water through it. And what's normally done is to run this relationship with densities at the if you have a three-dimensional one, you break it up into plane. With the densities of each layer, calculate the transport of salt, and then feed the salt, then you say the density is equal to a constant plus another constant times the salinity. The way it's typically done. Then you put the density back in for each layer here and run it again. So the process either is a marching forward process or sometimes, depending on how you go, an iterating process. The important thing is to couple it so that you wind up with densities. And out of this, then, you get, well, first of all, I should say, in addition to the initial and boundary conditions, you have to supply the velocities from the hydraulic model. Usually you find the dispersion coefficients from the ones that work for the salt, which you found here for this. When you fed this back in to get the densities, you wound up with some dispersion coefficients. So you get this, these also from the hydraulic model, the hydraulic and salt model. And out of that you get concentrations. Now the sources and sinks. The sources are erosion from the bed, and the sinks are deposition of the bed, plus all the other external sources. So we have a problem with the bed because, as you recall, the bed changes in density with depth, and the procedure then is to simulate the bed as a succession of layers that sediment settles to, and that as it becomes covered, it consolidates. And then when erosion takes place, you erode layer by layer, it's bulk erosion, or you erode through the layer, it's surface erosion. And if critical shear stress is less than critical value for surface erosion, it doesn't erode at all. This results in a huge bookkeeping problem, because you have to keep track of layers that were put down and partially uncovered, and then other layers added to those and the consequences. Fortunately, the change in the surface and the properties of sediment take place in just a short distance for the most part. So you wind up with 2 or 3 layers carrying most of the action. This is the hardest part of the sediment transport, is the keeping track of the bed condition. Okay, so we have let's say a little more about the sources and sinks while we're at it. We can write for the erosion part. Write HDC CDT. This equation once thinks in terms of the CDT. The sources and sinks have to be CDT. I'll put it in this form for convenience in a presentation. HDCDT is equal to some constant times the shear stress on the bed divided by critical shear stress for erosion minus 1, or tau of 0 greater than tau critical, and less than tau critical for bulk erosion, so B. And then, of course, if it's less than tau critical, it's 0. And then for bulk erosion, you change HDCDT. Is equal to this is the concentration of particles in the bed times the change in depth of the bed times the layer of the bed. And this is, of course, per unit area of bed. And then the deposition. For tau, let's say at H, you see is equal to, let me see this, C times 1 minus tau over tau critical for deposition. For tau less than tau critical for deposition. Then accumulation on the bed we have. The accumulation, I'll call it change in depth. What do they call it? D there. This way. Is equal to the depths of water, same depth here. Divided by the concentration of sediment in the bed times the integral from 0 to delta T of dCdt. In other words, as this flux of material goes to the bed, accumulates on the bed, then the thickness that it makes is that mass that goes down divided by the concentration of particles. Well, there are some real problems with this model, with this equation. And I'd like to describe a few of them. First of all, this term is the one that gives trouble in computation, just like the linear momentum, the momentum part of this hydraulic equation there. The unknowns tend to accumulate in D. That is, D has an effect on it, and there isn't any way to really pin it down other than the salinity. And if you have numerical dispersion, it appears in this D. So if you wind up with odd-looking dispersion coefficients, you've probably got some problem with the numerical system. The relation is not very stable when there's a sharp change in concentration. It tends to oscillate when there's a sharp change. So if you have a front, let's say, a concentration, or this is actually concentration, something like this, with distance, but it will show something like that, unless you have very short time steps. To get around that, there have been a number of schemes. One is to compute this separately from that and do it at alternate time steps. That is kind of split the computation up. Another one is what they call upwinding, which is trying to adjust it, the concentration back, that is, smooth it out behind it. And there's been a whole lot of means tried to reduce this instability. But if it's a change in concentration is reasonably gradual, then it represents it pretty well. Unfortunately, this isn't too often a problem. Another problem, perhaps an even bigger one, is the settling velocity of the aggregate. The transporter is very sensitive to this term. And unfortunately, there hasn't yet been developed a good way to nail it down. Approaches that are used are, one of the best approaches been used, is to go out and survey past accumulations, model the system and find out what settling velocities cause that accumulation. Then that's the most reliable way to do it. Another way is to go out and take a device called an Owen's tube, which is just a long plexiglass tube, usually about 3 or 4 feet long, and maybe 4 inches in diameter. It has a mechanism so that you can close both ends, and it's lowered down, and the water is allowed to flow through it, and then at whatever depth you're interested in, the ends are closed off. It's brought up to the ship and turned upright, and settling velocity is measured by any one of several methods. You can just take samples out of the port and calculate your settling velocity. It turns out that even this, where you have minimum handling of the sediment particles, that is, you sampling right on the device you're going to make the measurement in, even that seems to destroy some aggregates, some of the bigger ones that settle fast. So, let's call it Owen. Sampling. It works pretty well for sampling during the strength of flow, when the aggregates are subject to some stress. But at times near slack water, when a lot of material settles, very fragile aggregates will form. And the recent measurements in the Thames estuary in Holland, and the Thames in England, have shown that those big aggregates, even those are destroyed. The measurements that showed it are video cameras or vidicons connected to a tube that's lowered down and just held in the water, and particles settle into it, and you measure the settling velocity optically this way. And it shows that there are larger particles. The Savannah River gator that I showed you also showed, from calculations of the settling velocity, that similar higher velocities occur than are found in the one tube. So the Owen's tube approach is the next best after actually modeling. And then finally, after that, you can use the relationship with the settling velocity is equal to some constant times concentration to a power. And I indicated 4/3 for flow in a flume, or where aggregation takes place in the velocity gradient decay, so that the weak ones are allowed to survive. But in estuaries, what's found is if you go out and make measurements in an estuary, plot log WS against log C, you get quite a range of values for the next one. So you want to use this with some caution. One way that you can use it is to use it and then make a measurement on an existing system, and the concentration that you wind up with will account for that deviation. So they're measuring the concentration, determining settling velocity from the rate of deposition in an existing system, running your model, verifying it, or calibrating it. This is really the best way.
So would those lines be from flumes, or would they be in different systems, or in one system at different times? The variation.
Oh, the differences? It's a difference in the history of the way the aggregates were formed. If they're formed in the mixing zone where there's a vertical settling against it, there'll be weak aggregates, and this will be like this.
Yes.
And if they're in an area of high water aggregates, then possibly with a flash. The history of the aggregates is pretty hard to say that at any instant that they're directly related to concentration by some simple calculation. Well, this is a thumbnail sketch of modeling. And I made it. If you get a group of modelers together, you will get lots of discussion. And if you just get 2 or 3 of them together, you get a lot of discussion. We have some of the world's best right here. Professor King developed the models that are used by the some of the models that are used by the Watershed experimentation. Professor Orlov's developed hydraulic water quality models. Professor Rock has done some modeling. And this first 2D sediment model was one of our doctoral students, Ron John Larry Thury. And that's still used by the waterways experimentation. That was developed in '74, so it's had a pretty good life. And it's been used in over 100 applications. Still has problems that we'd like to improve. And Lisa, some of you may know Lisa Ruick. She's working on improving it at the waterways experimentation. I'm happy about that. In spite of their shortcomings, they're very useful. It's good to point out their shortcomings, but it's important also to realize that even with their shortcomings, they're far better than trying to do without them. The alternate is to experiment on the prototype, to say, well, let's go out and now not divert any more water, see what happens. That's very expensive. Or if you put a jetty in the wrong place, you're talking about tens to hundreds of millions of dollars. You can't afford to put it in the wrong place. You need to use some system of calculated where it is. So in spite of their limitations, they're still far better than alternatives. That's it. Well, this is the day we've all worked for. I must say I've enjoyed it very much.
Thank you.
I'm a little at a loss to have you all watch TV and try to figure out where you are. And not having had the previous course with you, handicap. Sorry about that. Well, y'all have a Merry Christmas. And thanks very much for the present. I appreciate it. Very nice.